21 ECC 202T Analog and Linear Electronic Circuits. Unit 4 Different types of filters: low pass filter, high pass filter, band pass filter, and band reject filters. Filters. A filter is used in electronic systems to control signal frequencies. It selects the desired frequency range and removes unwanted noise or interference. Passive filter. Passive filters are made using R, L, or C components. Passive filters are simple in design and low in cost. It cannot amplify the signals, it only attenuates unwanted frequencies. It is commonly used in basic electronic circuits. The active filters uses op-amps or transistors with resistors and capacitors. It can both filter and amplify signals. It has better performance at lower frequencies. It is widely used in audio systems and communication devices. Advantages of active filters. Flexible gain and frequency adjustments. In passive filters, the signal strength decreases after filtering. Active filters solve this by amplifying the signal while filtering. Their design also makes changing cutoff frequencies easier. No loading problem. Loading occurs when one circuit stage affects another. Since active filters uses op-amps with high input impedance and low output impedance, signal transfer becomes efficient without affecting connected devices. Cost effective. Passive filters often needs inductors which are bulky and expensive. Active filters avoid inductors and use low-cost op-amps, making them smaller and cheaper. Applications of active filters. Active filters are widely used in various electronic and communication systems. Communication systems. Active filters help to remove unwanted signals and improve signal quality in communication devices. Signal processing. Used to filter noise and extract useful information from input signals. Radio and television. They select desired frequency channels and eliminate interference for clear audio and video transmission. Telephone networks. Active filters improve voice clarity by reducing noise and unwanted frequencies. Radar systems used for accurate detection and processing of reflected signals in radar applications. Space and satellites. Active filters ensure reliable signal transmission and reception in space communication systems. Biomedical equipment used in devices like electrocardiogram, that is ECG, and electroencephalogram, EEG machines to remove noise and obtain accurate biological signals. Commonly used filters. The commonly used filters are low pass filter, high pass filter, band pass filter, and band reject filters. Low pass filter or LPF. They used when only low frequency signals are needed, such as in audio applications to remove high frequency noise. High pass filters used to remove low frequency noise or unwanted DC components from the signal. The frequency response of low pass and high pass filters are shown in the figure. The passband and stopband are two important terms used in the frequency response of the filters. These terms define how a filter behaves. Passband desired frequency range allowed through. Stopband is the unwanted frequency range blocked by the filter. Bandpass filters. Bandpass filters pass only the frequencies that fall between its values of the lower and upper cutoff frequencies. Bandstop or notch filters eliminate all signals within the stop band while passing all frequencies outside this band. The frequency response of bandpass and bandstop filters are as shown in the figure. Next we are going to analyze the low pass filter in detail. The circuit diagram for the low pass filter is as shown in the figure. The filtering R and C components are connected to the non-inverting terminal of the op-amp, and the frequency response is also given in the right hand side of the slide. The low pass filter allows low frequencies to pass and attenuate high frequencies below cutoff frequency. The output remains constant below the cutoff frequency, and above FC the output decreases at 20 dB per decade for the first order low pass filter. Next we are going to see the derivation for the low pass filter. So we have the RC network in the input side. The capacitive reactance is given as Xc is equal to 1 by j omega C. Using the voltage divider rule, we can find out the output voltage. Vout is equal to Vi into Xc by R plus Xc. By substituting the value of Xc, we can get Vout is equal to Va into 1 by j omega C by R plus 1 by j omega C. After simplifying, we can get the Vout by Va as 1 by 1 plus j omega Rc. This is the transfer function of the first order low pass filter. The cutoff frequency is given as Fc equal to 1 by 2 pi Rc. For a first order low pass filter, the transfer function is given as h of j omega equal to 1 by 1 plus j omega Rc. We know that omega equal to 2 pi f, and corner frequency is given as Fc equal to 1 by 2 pi Rc. By substituting these into the transfer function equation, we can get h of f is equal to 1 by 1 plus j into f by Fc. The magnitude of this transfer function is given as magnitude of h of f is equal to 1 by root of 1 plus f by Fc the whole square. Here f is the input signal frequency and Fc is the corner or cutoff frequency of the filter. So we have the transfer function of low pass filter h of j omega equal to af by 1 plus j into f by fh. So the magnitude is given as af by root of 1 plus f by fh the whole square. Here af is the pass band gain of the filter and fh is the cutoff or corner frequency. The magnitude response is given as h of j omega is equal to af by root of 1 plus f by fh the whole square. This shows how output gain changes with frequency. The phase angle is given as phi equal to tan inverse f by fh. It represents the phase shift between input and the output signals. The condition at different frequencies. Next we are going to look into the low pass filter response for different frequencies. When f is lesser than fh, output gain remains almost constant. So the magnitude of h of j omega will be almost equal to AF, and this region is called pass band. When f is equal to fh, the output becomes the magnitude of h of j omega equal to AF by root 2, that is equal to 0.707 AF. This is called the cutoff point or minus 3 dB point. When f is very much greater than fh, the output gain decreases significantly. The magnitude of h of j omega will be lesser than AF. This region is called the stop band. The roll off rate. Gain decreases at minus 20 dB per decade for a first order filter. This means for every 10x increase in the frequency, the output reduces by 20 dB. Next we are going to analyze high pass filter or HPF. The first order active filter is given as shown in the figure. The frequency response is also shown in the right hand side of the slide. It has a capacitor and resistor network at the input side. The capacitor blocks low frequency or DC signals. The resistor helps to form the RC network. The op-amp improves gain and avoids loading effects. So in the frequency response graph, we can see below FC the output is very low, that is attenuated. At FC the output reaches 70.7% of maximum, that is minus 3 dB point. Above FC the output remains almost constant. For a first order HPF, attenuation is 20 dB per decade below the cutoff frequency. The working principle of high-pass filter. At low frequencies, the capacitor reactance Xc is high, so it blocks most of the input signal, resulting in very small output. At high frequencies, the capacitor reactance decreases, allowing the signal to pass easily, so the output increases. The transfer function of the first order high pass filter is given as h of f is equal to j into f by fc divided by 1 plus j into f by fc. This equation shows that the filter passes high frequency signals and attenuate the low frequency signals. The cutoff frequency is given as fc equal to 1 by 2 pi rc. At this frequency, the output voltage becomes 70.7% of the maximum output. The transfer function of the high pass filter is given as h of j omega equal to af into j into f by fl divided by 1 plus j into f by fl. So the magnitude is given as magnitude of h of j omega equal to af into f by fl divided by root of 1 plus f by fl the whole square. Here af is the passband gain and fl is the lower cutoff frequency. The magnitude of this high pass filter shows how output gain increases as frequency increases. The conditions at different frequencies is as given as follows. When f is very much greater than fl, the output gain is almost constant. That is, the magnitude of h of j omega will be almost equal to af. This region is called the pass band. When f is equal to fl, output becomes magnitude of h of j omega equal to af by root 2, that is 0.707 af. This is the cutoff frequency or minus 3 dB point. When f is lesser than fl, output gain becomes very small. That is, the magnitude of h of j omega will be very much lesser than af. This region is called the stop band. The gain of the HPF of a first order decreases at minus 20 dB per decade below the cutoff frequency. This means every 10x increase in frequency causes output to reduce by 20 dB. Next we are going to look into bandpass filter or BPF. The bandpass filter allows signals within a specific range of frequencies to pass while blocking frequencies outside that range. We have two different types of the bandpass filter. First one is narrow bandpass filter and other one is wide bandpass filter. Narrow bandpass filter has a high Q value. Q is the quality factor or figure of merit. So narrow bandpass filter has high Q value which is greater than 10. The bandwidth is very small. This narrow bandpass filters used when selecting a specific narrow frequency range such as in radio receiver systems. Wide bandpass filter has a low Q value which is lesser than 10. The bandwidth is wider. These filters are used where a broader range of frequencies is needed. The quality factor Q indicates the selectivity of the filter. Higher Q means narrower bandwidth and better selectivity. Lower Q means wider bandwidth. The Q factor is given as FO by bandwidth. If that is bandwidth is given as FH minus FL, and FO is the central frequency and it is given as root of FH into FL. So FH is upper cutoff frequency and FL is lower cutoff frequency. Wide bandpass filters. A wide bandpass filter allows signals within a broad frequency range to pass while attenuating frequencies below and above that range. The circuit is as shown in the figure. It has a combination of high pass filter and low pass filter. This high pass filter blocks low frequency signals below FL and allows higher frequencies to pass. The low pass filter stage blocks high frequency signals above FH and allows lower frequencies to pass. When both the HPF and LPF combine, it only allows the frequencies between FL and FH to pass through the circuit. This creates the bandpass region. The roll off rate. At lower frequencies, gain increases at plus 20 dB per decade. At higher frequencies, the gain decreases at minus 20 dB per decade. The applications of wideband pass filters are in audio amplifier systems, communication systems, signal conditioning circuits, and biomedical signal processing. Next we are going to look into band reject or band stop filters. The band reject filter removes or attenuates signals in a particular frequency band while allowing both low and high frequencies to pass. Working principles. The signals with frequencies below FL are passed. Signals with frequencies between FL and FH are blocked or attenuated. The signals with frequencies above FH are also passed. This creates a rejection band or stop band between FL and FH. We have two types of band reject filters. One is narrow band reject filter and second one is wide band reject filter. The narrow band reject filter is also known as notch filter. It rejects a very small frequency range, commonly used to remove 50 or 60 Hz power line noises. Wide band reject filters rejects a large range of frequencies used in communication and signal filtering applications. These band reject filters are used in noise removal systems, audio processing, communication systems, and biomedical equipments. Next we are going to see how to implement a narrow band reject filter. A narrow band reject filter, also known as notch filter, can be implemented by subtracting the output of a narrow band pass filter from the input signal. The working principle is the input signal is applied to the circuit. One path goes directly to the summer, that is adder or subtractor. The second path passes through the narrow band pass filter, which selects only a small frequency band around the central frequency FO. This selected narrow band signal is then subtracted from the original input signal. As a result, the particular frequency band is removed, producing band reject output. The waveforms are as shown in the figure. Next we are going to see some of the problems on filters. First one is a first order high pass filter uses a resistor 5 kilo ohm and a capacitor 0.02 microfarad. Find its cutoff frequency. For a first order high pass filter, the cutoff frequency Fc is given as 1 by 2 pi Rc. By substituting the values of resistance and capacitance, we can get Fc as 1.59 kHz. Next problem is based on the bandpass filter. A bandpass filter has a lower cutoff frequency of 500 Hz and a upper cutoff frequency 2500 Hz. Calculate the bandwidth and center frequency. The bandwidth is given as fH minus fL. So from the given upper and lower cutoff frequencies, we can get the bandwidth as 2000 Hz. And the center frequency is given as FO is equal to root of fH into fL. By substituting the values of fH and fL, we can get the center frequency as 1118 Hz. Thank you.